Algebra 1. We are starting a new chapter, Chapter 8. And Chapter 8, the big picture is we're going to do a lot of factoring, but we're going to start factoring polynomials. And so we'll see what that looks like as we go along. This first lesson just kind of eases us into factoring monomials and what that looks like, and also finding the greatest common factor that will be one of the key tools that we will use. So let's jump in. So this is 8.1. Oh, gotta put my, there we go. 8.1, and it's called monomials and factoring. Monomials and factoring. So factors, we call the things that you are multiplying in order to create a product. And so we're going to be looking at kind of like multiplication in reverse, in a sense, of like what different things would have multiplied to create what we got. So let's first of all, though, define the term factor. Factor. We could say it is a value. Depending on where you look, you might see like a number that divides into another number, but we're not necessarily dealing with numbers here. We're dealing with both numbers and variables. So I'm just going to say a value that divides into another value with no remainder. No remainder. You might have heard that put before as like divides evenly into. That's another wording that is used sometimes, but just to avoid any confusion with using the word even there of like, oh, so it has to be an even number. We'll say that it divides into another value with no remainder. Now you should have done this with numbers for quite a few years now. We're going to be doing it now with numbers and variables. And so let's just look at some examples. The first section says to factor each monomial completely. To factor completely means to represent the smallest things that could have multiplied to create the term that we're dealing with. That'll make more sense once we look at some examples. So let's just jump into one of these factor completely kind of problems. Factor completely. And we'll do this one first. 15 x cubed y squared. Okay? Now for factoring 15, we'll do that first. You might have different ways that you've learned how to do it. I find that most students have learned and prefer a factor tree where you like start with 15. You're like, well, what two numbers could multiply to create 15? And we get to a 3 and a 5. And then we look at whether 3 or 5 can be split apart into two different things that could multiply. And 3 and 5 are both prime numbers. There's nothing that divides into them other than 1 and themselves. So 3 is 1 times 3. That's the most that you could do. 5 is 1 times 5. So we just leave it at that. Then if I do my answer, I guess I could have done that part in blue, but yeah, pretend this is in blue because like this is my work. Why is that not selected? So we had 15 here, and we said that is 3 times 5. Okay, so that's as far as we can go with the number. So 15 x cubed y squared we can represent as, that's not what I want a 3, as 3 times 5 times, now what's x cubed but x times x times x, so x times x times x, and then y squared is y times y times y, and that is our answer. We have completely factored this. None of those factors that we have there can be factored any further unless you start to get some remainders going on. Okay, that's that one. Let's do one more of the same kind of problem. This one we have negative 44. x, y squared, z. All right, well, let's do the number first, negative 44. So negative 44, I like to pull the negative out first. So I like to do negative 1 times a positive 44. And then, well, what's 44? Let's see, that's divisible by 2. So that can be 2 times 22. And 22 is another even number. I always like to check first, is it an even number? And I can divide by 2. 22 is 2 times 11, and 11 is a prime number, so that's as far as we can go. So what we have here as factors is a negative 1, a 2, and an 11. Okay? So then this can be represented as negative 1 times 2 times 2 times 2 times 11 times x times y, because it's y squared, and then times z. And that is it. We're done with that one. We have completely factored it. This complete factoring we will use as a tool for the next kind of problem that we're doing. At least it'll be an optional tool that might be helpful for some of you. Okay? All right, so next we need to talk about what a GCF is. This is kind of a new little section. GCF stands for greatest common factor. Now, we already defined what a factor is, so we don't need to redefine that. We can go ahead and use that term in our definition. And I'm going to define it this way: the largest factor that two or more values have in common. The largest factor that two or more values have in common. All right, so we're looking at two or more things. In this case, we're going to be looking at two or more monomials and saying what's the biggest thing that can multiply into these two or more monomials evenly. Or I could say without a remainder, like we did before. So let's look at some examples. I have, I think, 3 examples here, and that'll do it for this lesson. Then you can get started on your homework. So let's find the GCF. So these are in the instructions. Find the GCF of each set of monomials. This would be, I'll just say, find the GCF, the greatest common factor. And let's do it with this. Let's go with a 6x squared y cubed and a 12x cubed y. Okay, so 2 methods. Method 1 would be to completely factor each of these. So let's completely factor this. And if we did the factor tree, we would get the 6 is 2 times 3, which those are both prime. So I'm just going to jump straight into this is 2 times 3 times x times y times y times y. Okay, so that's that one completely factored. Let's completely factor this one. Well, 12 is 6 times 2, so we just need another 2 in there. Or in other words, if I divide 12 by 2, I get 6. Then I divide the 6 by 2 and I get 3. So I have 2 times 2 times 3 times x times x times x times y. So for finding the GCF, you can start out completely factoring, like we just did, and then you can look at what do these complete factorizations have in common? Well, let's see, they both have a 2 in them, so I can use a 2 from each of them. And that gives me a 2. And then let's see, so the one on the right has another 2, but the one on the left does not. So I can't use that. Let's see, the one on the left has a 3, and the one on the right has a 3. So they both have a 3. So I can use a 3. Now let's look at the variables. Let's see, I'm using an x here and an x there, so they both have an x. And there's another x here and there, so I can use an x there and there. They both have a second x. And the second one, the one on the right, still has another x, but the one on the left does not have any more x's. So I can't go any further. The one on the left has a y, and the one on the right has a y, so they both have a y. Oops, sorry about that. They both have a y. So I'm going to use a y from each of them. And that's all. The one on the left has y's, but not the one on the right. The one on the right has a 2 and an x, but there's not a 2 and an x on the one on the left. So I multiply this out and I get 2 times 3 is 6. X times x is x squared. And y, 6x squared y. Hopefully you can see the yellow on the screen just fine. I'll write that in blue just in case that helps. 6x squared y. Okay, that's how to do it with completely factoring and then looking at what they have in common. Method 2 is for those of you who just have a better sense and you're a little bit better at just being able to look at and to figure things out. We could look at this and be like, well, let's see, what are the numbers 6 and 12? What's the biggest thing that goes into both 6 and 12? Oh, 6. Okay, so I have my 6. Then let's look at the x's. What's the biggest thing that goes into x squared and x cubed? Oh, an x squared. With the variables, if they both have the same variable, you can just go with whichever exponent is the smallest that you have. So we have an x squared and an x cubed, so they both can factor an x squared. Then we have a y cubed and a y. Well, a y is what we would pick. So we get the x squared from the left, the y from the right, and that's the biggest thing that we can do. So you can also jump into a straight like that. Have on your radar the way to completely factor like this, though, and how to get the GCF by completely factoring, because there are some problems later where this might be a helpful tool. Okay, let's do our second example of this kind of problem. Same thing, completely factor. This time we're going to do 4c squared d and 7xy cubed. All right, let's completely factor these. 4 is 2 times 2. So we have 2 times 2 times c times d. That's that one. And then 7 is a prime number, so that's just 7 times x times y times y times y. Okay, let's look at what they have in common. The one on the left has a 2, but the one on the right does not. Okay. The one on the left has a C, but the one on the right does not. The one on the left has a D, but the one on the right does not. The one on the right has a 7, but not the one on the left. The one on the right has an X and then a Y, but the one on the left does not. They have nothing in common. Well, there is technically one thing that they have in common. 1. They have 1 in common. Right, because the one on the left, we could say it's a 1 times 2 times 2. The one on the right, we could say it's a 1 times 7 times x, etc. And a 1 is common to both of these. And sometimes that's the most that you can get. All right, one more example. Let's go with 9xy squared and 18yz and 21 x squared y cubed z. All right, so if we completely factor these, 9 is 3 times 3. So we get 3 times 3 times x times y times y. Yes, that one. 18. If you wanted to, you could always do a little factor tree. 18 is 2 times 9, and 9 is 3 times 3. And so I have 2 times 3 times 3. This is a 2 times 3 times 3 times y times z. And I'm going to make this third one a negative 21. Let's make that a negative 21. Just for kicks and giggles. All right. So a negative 21, well, let's see. What is that? That is a negative 21 is negative 1 times a positive 21. 21 is divisible by 3. Little tip if you didn't know, you can take a number like 21 and add the 2 and the 1. 2 plus 1 is 3. If, when you add the digits of a number, they are divisible, if the number that you get is divisible by 3, then the number that you started with is divisible by 3. In other words, let's just say like the number 231. Number 231. If we add the 2 plus 3 plus 1, we get 2 plus 3 is 5, plus 1 is 6. 6 is divisible by 3. That tells me that this big number that I started with, 231, is also divisible by 3. Well, divisible by 3 trick if you didn't know it. So 21 is 3 times 7, and 7 is prime, so that's as far as I can go. So negative 21 is negative 1 times 3 times 7. Then I have this times x, because it's an x squared, and then times y times y times y, because it's a y cubed, times z. Okay? So let's look at what they have in common. The first one has a 3. Oh, they all have a 3. All right, well, let me try red. So I can pull a 3, 3, 3. I can pull a 3 from each one of them. The second one has another 3, but the first one has another 3, the second one has another 3, but not the third one, so I can't use another 3. Do they all have an x? The first one has an x, but not the second one. Okay, so x isn't going to work. How about a y? The first one has a y, second one, they all have a y, so y, y, y. All right, there's another y in the first one, but the second one does not have any other y's. So there's nothing else left that they all have in common, so 3y is as far as I can go. Now, if you did that to looking at it, you might be like, let's see, 9 and 18, well, those both have 9 in common. 9 goes into 9, and 9 goes into 18. Oh, but 9 doesn't go into 21. But let's see, 21 is divisible by 3. And 3 goes into 9 and 18. Oh, so 3 is the biggest number that can go. And let's see, the first one has an x, but oh, the second one doesn't have an x, so x isn't going to work. First one has a y squared, second one has a y. Okay, so a third one also has a y. And so they all have y's, and the smallest power of y that I have here is a y to the first. So y to the first, and I already determined that x doesn't work because it's not in the second one. There's a z in the second and third one, but not the first. So 3y is as far as I can go. Anyway, so 2 different methods to do those, and that is lesson 1. Hopefully that makes sense. And yeah, go ahead and get started on it. Hopefully you get most, if not all of it done. And Tuesday will be our review day for this lesson. All right, hope it goes well. Bye.